glacier.
Okay. Hello, everyone. Thanks, Nick, for setting me up pretty well for this talk. I'm Rob, a postdoctoral research fellow at the University of Bergen. At the moment, I'm working with Andreas Born and others using radar isochrones to improve our understanding of Greenland ice sheet motion. But before this, I completed my PhD at the Scott Polar Research Institute in Cambridge. This work was born as the last chapter of my thesis, using bed topography data from Nick and supervised by Paul. But before we get to the Antarctic part, I'd like to take you on a quick visit to Greenland. So with the Responder project, I did some borehole and numerical work looking at Cermak Kujalek or Store Glacier on the west coast. And these boreholes revealed variable deformation and variable thickness of temperate ice. That's the borehole site. I wanted to understand why these variations happened, so I built a model in Elmer ice to explore them in a bit more detail. A major outcome of this work was showing just how much intermediate scale topographic variation can influence patterns of ice deformation. I found that basal sliding can go from nearly 100% of surface velocity to nearly 0% over a few kilometers or even less. So I wanted to try this out in a region where we have high-resolution bed data beneath an existing ice sheet, and Nick's data and Thwaites were an ideal location for this. Before location specifics, though, I'll highlight a couple of salient points about the model. 37.5 meter horizontal resolution, so quite high in that respect. Coulomb sliding, and an N4P formulation with full treatment of temperate ice and very high vertical resolution towards the bed. I direct you to my previous paper for full methodology, but essentially I look at a box and adjust the slope rather than the basal traction field to arrive at the average surface velocity of the region of interest. So this brings us to Thwaites. As I'm sure you know, Thwaites is kind of funky for several reasons. We have an inferred extensional rift basin comprised of blocks and basins oriented perpendicular to flow. This is in contrast to the Sipple coast ice streams that have a fairly isotropically smooth bed throughout. We have lots of surface geophysics, but no boreholes, and it's expected to be quite important for past and future ice sheet mass loss. So this slide shows the study area and the sites I used. Does this pointer work? Yeah, so these are the sites. And as I mentioned already, and as Nick nicely explained, this is from that data. And then already there are some kind of neat inferences that can be made. High driving stress and high basal traction broadly map to topographic highs. They also map to regions the radar indicates are rough, with an absence of streamlined bed forms. So, can the model tell us anything interesting about basal motion at Thwaites? How important is subglacial topography? Will that relate to distinct banding in inferred basal traction? And are any of these aspects related back to subglacial morphology? I'll invert the normal order and get straight to results, and then we can look at the reasoning. Basically, I expect basal motion to be really variable in rough sections of Thwaites, but much more uniform over subglacial landforms interpreted to be MSGLs. I also find it difficult to avoid the conclusion that there is probably quite a substantial amount of temperate ice beneath at least parts of Thwaites Glacier. And overall, the basal motion I modeled is defined by an interplay between rough and smooth parts of the bed. Which brings us to the supporting results. In the top left, you can see the close-up map. So keep an eye on the orange box. This will change throughout the rest of the presentation and highlight the location or locations being discussed. So first up, we have uplineation with 3 panels again, and these are going to remain consistent. The lowermost panel is bed topography. It's all exaggerated by a factor of 3. Above this is normal stress at the base and then basal velocity. Here, the tendency of more prominent topography to have heightened basal velocity compared to depressed regions is already visible. Overall, though, the pattern is not too remarkable. This changes quite dramatically for up canyon, and note a change in velocity color bar scale 2, where much more spatial variability in basal velocity is evident. Note that given the topography, these are inferred to be more resistant erosion-driven features, as explained by Nick earlier as well. To take you on a quick aside, the classic Halle 1981 paper proposes that abrasion is controlled by basal velocity and subglacial sediment concentration. We don't really have a control for subglacial sediment content and can expect it to remain fairly constant over the areas we're discussing. So basal velocity alone is a reasonable proxy for total erosion potential, which is well supported by U-shaped valley morphology. Bringing this to Thwaites indicates that basal velocity alone cannot be the primary control on these rough sections of subglacial topography, which leads me to the conclusion that pre-existing geological heterogeneity is one of the main deciders. Throw in a little bit of subglacial hydrology as well, which I'll elaborate on further in a forthcoming paper. In a way, this makes our lives easier. Even after at least 100,000 years beneath an ice sheet, the topography of inferred bedrock regions is effectively stochastically determined by things we have no way of easily modeling. Last, looking at down over deep, this feature has this intriguing trough and prominence feature here. As with the canyon, basal velocity is at a low in the depressions and at a high in the prominences. Such a feature has been modeled in 2D. This is just a plan view of the same section. So this has been modeled in 2D with Ali and others suggesting high normal stress will increase ice bed coupling upstream and decrease it downstream, resulting in the over-deepening. So we can't rule this out, as it's possible the subglacial landform I model here is in a steady state and had a different stress field prior to this. But from this alone, I don't find direct support for that hypothesis. And normal stress is actually a minima inside the trough. So next we have deformational variability and temperate ice. Here I'm skipping up lineation as it's a bit less interesting and I don't have time. This panel shows deformation heating here, which is the product of the stress and strain tensors with the cold temperate transition surface in white. Basal velocity ratio in red, where 1 is all sliding, and 0 is all internal deformation, and synthetic deformation profiles which match the colored lines. At up canyon, we see a relatively thin temperate layer gradually develop as a result of topography forced deformational heating, which is most notable as the ice is forced over the canyon itself. Temperate ice is also readily apparent at down over deep, with very strong deformation heating over the trough itself. And here the deformation profiles are also somewhat or more closely akin to those modeled and observed on our previous excursion to the Greenland ice sheet. So to me, this is already enough to say we should expect some temperate ice beneath Thwaites, and hence funky deformation mechanisms that are not explicitly captured by existing basal motion formulations. The basal traction in the 2 rougher locations is already as low as possible for them to remain in local stress balance, but things become even more interesting when we consider the interplay between rough and smooth sites. So this figure warrants a bit of explanation, so please bear with. Each site is represented here, going downstream from top to bottom, and this shows the average temperate layer thickness across the domain in red, and the average basal velocity ratio, which we saw earlier too, in black. As we go right along the x-axis, the subglacial water pressure decreases, and the overall traction potential, or maximum traction that could be generated across the domain, paraphrased here as F, increases. The figures you've seen already have an F value of just about 1, meaning basal traction can just balance driving stress. However, considering the inferred basal traction field we saw earlier, we'd actually expect uplineation not to be in local balance, but to be supported by much higher traction at, among other regions, the rough elevated sites. So that's here and here. This can be emulated with an F value somewhat below 1, which is over here on the left. That should come up. Which will result in very low basal sliding and some quite thick temperate ice. So what does this tell us? Well, quite possibly that temperate ice is generated at rough rises, but can be eroded through smooth basins. It also suggests strongly that, very strictly speaking, the same basal motion relationship will not necessarily be equally appropriate across both sites, as Nick has just touched on as well. And there is no need to lean solely on subglacial water pressure to explain variations in inferred basal traction beneath weights. I hope that future work can place limits on the basal traction potential, given a set basal geomorphology and realistic pressure constraints. And that's all. Thank you. I hope this gets you thinking about complex motion beneath weights. Yeah, thanks.
Thank you, Rob. We have maybe one quick question. In the back.
I'm just trying to get Dusty's steps in this morning. So if you have 150 meters of temperate ice, that should stick out in the attenuation rates of radar data. So I guess what are the length scales of these temperate ice zones? Have you looked in the radar data to see if there's a fingerprint of these things?
I might come and talk to you about the radar data after this. That would be interesting. It's so in the model, I have to assume that the temperate ice starts at 0 at the start of the domain. I can change it a little bit. But yeah, I would be interested if anyone here has a good radar data set and can help me out with that one. That would be great.
You do.
I do. Super.
Next up, we have Guillaume